Okay. All right, let's get started. Thank you all for coming. My name is Kyle Wasberger. I'm the Principal Sports Scientist at Driveline Baseball.
I'm Alec Miller. I'm the Chief Technology Officer for S3D Incorporated.
And this is our applied session, learning to use Python a little bit. This is meant for those who have zero or near zero experience in Python. So if you have never even tried Python, this is for you. So we hope that you get some use out of it. We both found we had similar stories of not really using Python in school and then getting out of school and all of a sudden needing to have Python skills. So hopefully, if there are some students in the audience or watching the recording at a future date, you can gain a little bit leg up than what we had. So.
Yeah, and that's kind of where we wanted to start off. We wanted to ask the audience, who has experience coding in MATLAB and R? A lot of hands.
Oh,
now, who has experience coding in Python? One half of the room. We had the whole room, and now we just have half the room. So that's really what we're trying to highlight. There was a session, I think yesterday, about bridging the gap between academia and finding good employment. And this is one of the things that we would like to highlight, is because in our industry, we're looking for people who have good experience coding in Python, but also understand biomechanics. And those people that have those skills are few and far in between. And if you have those skills, you'll have a much greater likelihood of landing a position in the industry. So
next slide. For this workshop, we're going to be using data from the Open Biomechanics project, which was launched by Kyle Bodie and us at Driveline Baseball. It's a GitHub repo with accompanying documentation, S3D files and CSV files from 100 pitchers and hitters from our database. If you were at the baseball panel yesterday, you heard me talk a little bit about it. So if you haven't forked or cloned the repo already, please start doing so now. And yeah, I think we should start with, did everyone get through the, what's it called? The PDF?
Yeah, the PDF instructions, installation instructions.
No?
If you can't find it on the Wova app, there's a PDF that's attached to this session. So if you go and click on this session for today, you could take a look at the PDF and start following instructions to install Anaconda, install VS Code, and clone the GitHub repository for the Open Biomechanics project. That would be a good place to start. Otherwise, just follow along and we'll teach you some Python. So we should switch spots here. So Kyle's going to get started, and then about halfway through, we'll switch.
Forgive me, I don't. Setup tool. All right, so getting started. Obviously, I said earlier, the purpose is to introduce everyone here to beginner Python and some sports biomechanics uses. The first thing we can do is learn how to import some packages. So we can start with import, simple command, and then OS. OS is a very standard, what does it even stand for? Operating system, yeah. Import OS. It's a package used for setting file paths and a lot of other cool stuff. And
I'm just going to interrupt Kyle for a second. If you're new to coding in general, typically at the top of your file is where you would import all of your necessary packages for your code. And then you would define any like discrete metrics or values that won't change in constant variables. Then you go into your more dynamic coding. So we're starting off with importing packages. That's a very typical way of starting your Python code.
Yeah. And yes.
Quick question: will this do enough?
Yes, excellent question. This will be made available after the session. Thank you. The other package we'll be dealing with mostly for this one is another popular one called Pandas. A cool thing with Python is that when you import packages, you can abbreviate them. So if I want to use a function within the Pandas module, like we will earlier, I don't want to have to type out pandas.function every time. So I can import pandas as something shorter to save me from typing pandas out over and over again later. And pretty standard one is to import it as PD. Another thing that good coding practice is to dynamically set your computer username. We can do this using the OS get login function. Live coding. So in a little bit, we're going to be setting file paths, and obviously in every file path is your computer username. So on my laptop, it's Kyle W. On Alex's laptop, it's Alec Miller. And so if you hard code that username into your code and then try and give it to someone else, they're not going to be able to, their computer isn't going to be able to find those file paths because their computer username is different. And so we can instead dynamically set this as a variable. I just can call it user. You can call it whatever you want. And then from there, we can set our git path. GitHub. Nope, you don't have to. Just kind of best practice if you want to give your code as an example to someone or share it. Yeah, good question. All right, so we can set our file path explicitly here. And this is, I should say, this is assuming you did the default install location for your GitHub repo. I'm going to type this out because I can't, and then explain it because I can't type and talk at the same time. All right, so now we've set our variable. I called it path GitHub repo. It's a character string. So if I get rid of the RF here, it's just a character string that shows where to get to users. Miller, GitHub, open biomechanics. So basically, we're just telling the computer, hey, this is where we're going to look at for all the data in the file explorer. And so we have to tell Python it's a file path with the prefix before the string R. So that tells Python several things, mostly how to handle backslashes or at least forward slashes. I don't know. And then another prefix we want to add to our string is the letter F. F allows us to insert variables dynamically into our character string. So now when Python reads this file path and sees this curly bracket and then the user variable, it's going to insert the user variable that we defined up here into that character string. Once we've defined that path, we actually want to change our script directory to that path. So that our computer will look into that file path for the files that we're going to list or the files that we're going to use. And then we can list the contents of that directory using os.lister. So now we have our first Jupyter cell complete here. We can go up to the left-hand corner here and hit run, and we get an error. See? Oh, not capital L. Lowercase l. No. Welcome to coding. What am I doing wrong? System cannot find. So it has 2 slashes, but user Alec Miller documents.
You can also show them how to set it.
Oh, it's users. Users coding on the fly. So, all right. So we did several things here. We set our user variable. If we want to just get, if we want to see what our user variable is, we can comment out the rest of this and just tell the computer to print user. When we do that, we get Alec's username, Alec Miller. Then we dynamically set the path GitHub repo character string, which inserted Alec Miller into that file path using the user variable. We then changed our working directory to that path, and then we once again listed the contents of that directory. When we do that, we get a list of folders, files, and hidden objects within that repo, or that file path, excuse me. So as you can see in the File Explorer here, we have a couple folders. We have an image folder, we have a gitignore file, and the license, README, and security markdown files. And sure enough, that's what we see here. All right, any questions so far? This can be pretty conversational and informal. So stop me if you're lost. All right, now we can move down one folder. We're gonna go inside this baseball pitching folder. And once again, we can OS lister the baseball pitching. All this is gonna do is air out lister. All this is gonna do is gonna take us one folder level deeper and then list the contents of that directory. So this would be analogous to clicking on the baseball pitching folder and then finding the contents of that folder. We've got 3 subfolders: code, data, images, and another README file. And sure enough, that's what we get listed out right here. All right, now we want to set the directory to where our data are. We can call that path data and OS path join. This is another function in the OS module that is pretty handy. We can give it baseball pitching and data. And so what this OS path join function is going to do is it's going to create a file path with these 2 folders. And that way we're going to be able to go all the way down inside this data folder. We can then list the contents of that path as well. And sure enough, we see that we've got some more subfolders and this file called metadata.csv, which is this guy right here. Now we can read in the metadata CSV.
If you're not doing this.
Yes. Yep. So to read in the metadata CSV, we use the Python with syntax. Join to our data path and then the file name, metadata.csv. We're got to supply the R, telling that we're just reading the file. This prevents us from accidentally editing the file. Metadata equals PD read CSV F. Okay, so let's take a moment to talk about this syntax. With in Python is a pretty standard syntax. Basically, it prevents you from leaving files open accidentally. It prevents you from reading or overwriting. And then so we supply this file path to the with argument. And then we're saying call this whole chunk here, this open chunk, call that F. So we're dynamically assigning it a variable. And then we're going to the pandas module, which we, again, abbreviated PD. And we're using the read CSV function to read in this metadata file. All right. So now we've got a variable called metadata down here. It's a pandas data frame. We can see that it's got 411 rows 411 rows, 10 columns. Doesn't make sense. All right. So first thing we can do to explore this CSV a little bit is use the pandas function head. So I call the variable metadata dot head function, and all head is going to do is it's going to show us the first 5 rows of the CSV dynamically in Jupyter. So we've got several columns here: user, session, session pitch. We've got subject mass, subject height, subject age, their plane level, and then on a pitch level, their pitching velocity, and then the corresponding C3D file names and the C3D model file that corresponds with the actual pitching trial. We can print the column names using print metadata.columns. This will print out a list of columns, which if you're not in Jupyter, you wouldn't have been able to see with the head function. We can use the shape function, metadata.shape, to print out the dimensions. Luckily, we're in Jupyter, so we have this information down here. But if you didn't and you wanted to explore the shape of your data frame, you can use the .shape function there. And then something you might want to do is find the number of users, session, and trials within the data frame. We can set num users equal to the length of the metadata.user column unique values. So using unique here. So metadata open bracket user, which is the column name that we're interested in, closing bracket, and then this dot unique function is just going to return us a list of all unique values in that column. Because the data frame is at a pitch level, obviously user is repeated for all the pitches within a user. We can then do num sessions using similar syntax. Sessions. Session. Not unique. So again, this metadata sessions.unique chunk is going to return us the unique values in the sessions column. And then this len function returns us the length of that list, which would be equivalent to the number of unique sessions. And then num trials do metadata session pitch. Unique. Closing parentheses there. And then we can print out this information. Print. Say we have, again, using the curly brackets, num trials, from sessions, and users. All right, so again, this is a dynamic string that we use the F prefix here, and we're just inserting these variables that we defined earlier into this print statement. When we run this, we see that we get meat data. Shows we have 411, which is this num trials variable from 100 sessions and 100 users. Lastly, we can find the average height and weight of our participants, something that you would need to do for an abstract. We can do average age equals metadata. Age years is our age column, and then use the mean function. So just same syntax as the dot unique function up here. We can use dot mean to find the mean of the values in that column. Average height, metadata session height meters, mean, and then average weight, metadata session mass kilograms, dot mean. All right, some more dynamic string defining here. We can do average participant demographics. And then we can add to the string by using the plus equals sign operator in Python. So all this is going to do is it's going to append whatever I put after this to the previous string. Page. Right, if we print this out, All right, so we can see that we got average participant demographics. The \n\t is just a new line and a tab character. So that tells Python when printing out this string to go down a line and then indent one level and then print the rest of this string. We can keep adding to the string by using the plus equals sign, the height, meters. So now we just added another line to our string, and we can see that our average participant height is 1.9 meters tall. Wait. And so now we added another line to the string to print out our average participant weight. Okay, so now, so that's kind of messing around with the metadata CSV. We can move on to the point of interest metrics CSV that is also in the repo. Yep. It's a 1. Yep. So this is just telling Python to format printing out the number to 1 decimal place. If we didn't have this 0.1f here, it would print it out to a bunch of decimal places like that. So it's formatting the print statement a little cleaner. Good question. So now we have to tell our computer where the POI metric CSV is. Again, going back to the OS path join. We already defined our data path, but then we want to go down one level into the POI folder. So instead of pulling in this CSV, we need to now go into the POI metrics folder and access this one. Same syntax here.
Is anyone running into any errors that they'd like me to come by and help with? So far, so good.
Okay, so similar syntax as when we read in the metadata CSV. We tell the computer where to find our CSV file. We call it F, and then we use the pandas read CSV function to read in that file. And by putting it within this with block, we're ensuring that the file gets closed after reading it in, and we're ensuring that we are only reading in the file and we don't have the ability to accidentally overwrite the contents. All right. Again, we can go through and mess around with our POI CSV, explore it, see what we got. We have session pitch identifiers. We have some pitcher level information like what hand they threw with, what the pitch type was, how fast it was. And then we have some point of interest metrics from our biomechanics pipeline, such as max shoulder internal rotation velocity, max elbow extension velocity, hip to shoulder separation angle, things like that. Yeah.
It gives you all the headers, and then it automatically just gives you 5 rows. Can you specify how many more rows?
Yep. So if I want to see 10 rows, I can put 10 in here. and it'll show me 10 rows. If I just want 1 row, I can do that. POI.
You can click on that. Cool.
Cool. Didn't even know that. So yeah, in Jupyter, if you're in the variable environment here, you can click on this button and view the whole thing just like you would pulling it up in Excel. Learn something every day.
Janelle, did you have a question?
You just show up this.
Yep, so the default behavior of the head function is to show 5 rows, but you can tell it exactly how many rows you want to see. There's also the tail function, which, as you may be able to guess, is the exact opposite. It'll show you the last 5 rows by default, but you can also supply custom number of rows to the tail function as well. And we can print the column names to see what we have in our data frame. So we have a lot more than the metadata, but we can open it up and see the full. The Jupyter will typically truncate long print statements like that. So if we're missing some, if we want to see them all, we can click on the open in a text editor, and it should open in another tab, and you can see all the columns just like that. Bye. So one thing we may want to do, since we have multiple throws from each participant, is we may want to get the average of all the POI values within each participant. To do that, we can use group by. So I'm going to define a new data frame called POI grouped, and I can use the pandas group by function and then feed it the variable I want to group by. In this case, that's session. And then from there, I can add on the dot mean function as well. And so this is going to go into our original POI data frame, aggregate all the values in the rows by the session value, and then I'm telling it I want the average. And then POI grouped. Again, we can use the head function to then see our data frame. We now have session over here as a row indexer. And now every variable, every numeric variable has been averaged within each session. So now session 1031, the average pitch speed was 94 or 90.4 miles an hour. Another thing you may want to do with the point of interest metrics is create a scatter plot. To do that, we can import the matplotlib package, pyplot as PLT. So again, here using this as PLT, I'm just telling Python that I want, every time I type PLT, I want you to know that I'm calling the matplotlib.pyplot module. To initialize our figure, we can use the PLT figure function. We can give it a fig size argument to tell it how big we want our figure to be. We can do a 10, this is, yeah, we can do 10 by 7. And then a thing I like to do is set my face color to white. So this will set the background of the plot to be white. If you don't do that, it just takes on whatever color of your Jupyter color scheme, and that can be troublesome with dark environments. Right, POI grouped. We're now going to call the pyplot scatter function. We want max shoulder internal rotation velocity on the x-axis, and let's do pitch speed on the y-axis. We can set a couple optional arguments here, like the size of the dots, the color of the dots. These are all optional, so you don't need to provide them by any means. Alpha will be the transparency of the dots. And then just to make them stand out a little bit more, you can set something called the edge color to black. When we do that, we get a scatter plot that looks like this. It's a good start to a plot, but we don't have any axis labels. We don't have a title, none of that stuff. So we can keep adding to our plot object using the PLT X label argument. We have shoulder, internal rotation, velocity on the X, and always good to put your units in the axis label. We can then give it a Y-axis label, pitch speed, and this is in miles per hour. Yeah. A what? Oh yeah, I haven't been in MATLAB in forever. Yeah.
Sorry.
It keeps adding.
Yeah. It will keep adding until you close that figure.
Adding a plot title now. We can do that. So now we got a title, we've got some axis labels. There are a bunch of optional arguments in the documentation, so you can adjust the font size, the font itself, where it's placed, things like that. And then if we want to just show the plot without the extra text here, we can use the plt.show function and get our scatter plot like that. I'll make it a little smaller so that we can all see it more easily. So that's a basic scatter plot. Another way we can visualize the data is a correlation matrix. To do that, we can import another package called Seaborn as SNS. First thing we want to do is we want to select the columns that we want in the correlation matrix. Call that columns of interest. And you can select any columns, but we'll just do a couple here. Pitch speed. We always want to see what's correlated with pitch speed, right? Max shoulder, internal velo, max elbow extension velo. We can just look at these. What we then want to do is create a subset data frame with just those columns. Subset data. Remember, we're working off of the POI group data frame. And then what I can do is I can pass into the brackets here the variable called columns of interest that we defined earlier. So subset data will now be that POI group data frame, but only restricted to the columns that I put in the list up there. We can then create our correlation matrix off of that subset using the core function. So that'll return a correlation, a diagonal correlation matrix between all the columns in our data frame. And then we can make another figure here. Do a square figure since it's a correlation matrix. And then we use the Seaborn module heat map function. Feed it the correlation matrix. So that'll annotate the plot for us. And we can do some optional arguments here to kind of spice it up, give it the colors that we want. And then, so the 0.2f here will tell Seaborn to only print off the correlation statistics to the second decimal place. You'll name Seaborn. Here we go. This is covered in the PDF. We need to, so when you start, you'll probably run into this no module named something. That means you just don't have that package installed. What we can do is we can say pip install Seaborn. And what that's going to do is it's going to install the Seaborn package, and we should be able to, it should work. I don't have to restart the kernel.
Actually,
Oh,
you kind of install SQL.
it didn't air out on the install. It aired out on the same. That variable called shoulder. Okay, so we had to troubleshoot there and install the Seaborn package, but now we're able to make this correlation matrix that I will shrink so we can see it and the code at the same time. And so what we have here is a diagonal correlation matrix between the variables we specified. And so it's a 3x3 matrix showing the correlation to two decimal places between our variables. So obviously we got 1 on the diagonals because the variable is perfectly correlated with itself. And then on the off diagonals, we have the correlation between the respective variables there. Again, I can keep adding to this list of variables or columns of interest. So I can say, maybe I want to investigate the rear ground reaction force peak. I can add that there. And it's not in there. What's it called? Magnets. How to know your variable names. And that added another row and column to the correlation matrix. And now I've got rear ground reaction force here. All right, last thing we'll do before Alec takes over is build a simple regression. First thing we want to do is import our stats package. Stats models. Stats models. Probably need to install that one too. Big one. All right, while we're waiting for that to install, we'll finish writing out our code here. Columns of interest, we'll overwrite that. We want pitch speed. We also want max torso, rotational velo, rear DRF mag max. So that's our peak rear leg ground reaction force, and then lead DRF max, and our peak lead leg ground reaction force. We want to drop POI grouped, which was again our old data frame, columns of interest. So again, we're just creating another subset data frame here. And then we want to drop any missing values. We can do that by using the drop NA function here. Right, we then want to split our data frame into our target variable Y and our predictor variables X. We do X, data, max, torso, rotational, velo, and lead, GRF, mag, max. So we're going to use these two variables to try and predict pitch speed. Right, we then need to add constant to our X data frame to account for the intercept. Then add constant. We can then fit regression. So we'll just call it model. We're going to just do an ordinary least squares regression model. We're predicting Y from X. And we want to extract the fit part of what that OLS function returns. And then we can print out our model summary. Also giving me this is fun. You see anything? Oops. Yeah. All right. So double brackets on that. All right. There we go. Sorry about that. So this prints out a bunch of information that you'd need if you were trying to analyze your data using Python and then report your results. Dependent variable is velo, ordinary least squares model. We get an R squared of 0.325, so meaning our independent variables of max torso rotation velocity and lead leg ground reaction force are accounting for 32.5% of the variance in our dependent variable of velo. And then you've got some more F statistics, p-value here, and some other summary stats. And then it gives you all the coefficients here. So your standard errors for those, your t-values, or your test statistics, and your p-values. And then your 25 and 70 or 95% confidence interval there. And then we can visualize the residuals from our model. Always good to inspect your residuals. Standard figure to speed along. Residuals, you can extract them from that model object. There we go. All right. That's supposed to work. Oh yeah. All right. So fitted values. Oh, I'm fitted values to the predicted value stuff. It's not a residual plot, but all right. I'm going over, so I'm going to turn it over to Alex here, and we're going to go through how to explore the full time series data. Yeah, that should.
Does anyone have any questions so far for Tyler?
I'm going to go over how to work with time series data. We're going to need some packages to go over. Kyle's getting my example code up, but we're going to be using import numpy as MP, import pandas as PD, we're going to be using matplotlib so we can plot .pyplot as PLT. There's a module called tkinter. Import tkinter. Actually, we're going to be pulling something from that module tkinter. So from tkinter, we can pull submodules within the actual module itself. So from tkinter, we'll import file dialog. From a package called SIPI, we will import integrate. And also from SIPI, we will import signal. And so what you could do is you could pull up your Anaconda prompt. Kyle pulled it up already, but just to debrief that real quick, if you search for Anaconda prompt, you can open that. It takes you into your base environment, but you need to get into your ISBS environment. So you can say Conda activate your ISBS 2023 environment. And then from there, you can say, you could use pip install. You can also use Conda install. Numpy, for example. And if you have it already, it'll tell you that you have it already. If you don't, then it will install it for you. So I would go through these packages that we're importing and make sure that they're imported in Anaconda prompt. Kyle discussed pretty extensively how to set file paths. We can also do this fairly easily too. If I want to set an object called force file to a certain location, I can open up my files and I'm going to go down to forceplate.csv. I'm going to right click on that and copy the path. And then I can paste that right in between my brackets. Kyle talked about the R value before the character string. That flips the slashes the opposite direction because Python expects them to be, I don't know the correct terminology, but like the forward slash, not this one. So Python will automatically flip that. And so if we wanted to, we could also set our directory to our joint angles file. To R, and we could go ahead and copy that joint angle CSV and paste it right in there. Now, if you don't want to code exactly, maybe you're building a Python application where you need to more dynamically select your file, we can do that with the tkinter module. So we have to set a main root for tkinter. And then we can say file name, this file name object will be whatever file we end up selecting. We can say tk.fileDialog.ask open file name is what it is. There's a couple options there, but it's file name. And then once we go ahead and select the file in our file explorer, we want to destroy the main root GUI that pops up. So if I go ahead and run this, down here you can see blinking my little tkinter GUI. If I open that, now I could go ahead and I could select a file, any CSV file, or really any file you want, but I'll just select the force plate CSV file. And if we want to leverage our Jupyter Notebook, we can see that file name has a value here, which is our force plate CSV. That's the file that I selected. And we also have force file in here and joint angles file. If we want to read a CSV file and assign it to an object, we will assign it to an object called master force data. And we can use the pandas module with the read CSV function. And we will do that for the force file. And we can take a look and see what this looks like. We could go ahead and open the CSV file and actually see what the CSV file looks like. Or I can take a look at my object in my Jupyter Notebook. I could find master force data, and I can open that in data viewer. And I can see all the different columns that I have that I can work with here. So we have index, session pitch, time. We have rear force X, Y, and Z. And we have lead force X, Y, and Z. And if we were to scroll through this file pretty deep, you can see that session pitch starts with 1031_2. And eventually we will get into other sessions. We got to go down pretty far though. Here you can see it switched to a different session, 1346.3. So there are thousands of force data points in this file, and we really only want to start analyzing force data from one session. So if we go back here, we can select data for only the first session. We can do trial force. We'll reassign the object as trial force data for one particular trial. And we can pull that from the master force data by doing a query function. And then in a character string, I can say what I want my query to be. I'm going to say session pitch, or where session pitch equals exactly. And I have to do this as a character string, 1031_2. So I'm using normal quotation marks to start this character string. And I want the character string to also include another character string, so then I can use just a single apostrophe. So now if I run this, down in my Jupyter Notebook, I should be able to see that I now have an object called trial force data. And if I go ahead to look at that, it looks exactly like our master force data, but we only have input from session that equals 1031_2. So it ends without adding more sessions. So now we can analyze force data from just a single session. Kyle had gone over plotting pretty extensively, so I'm just going to write the code here. We're going to plot for X, trial force data, and we're going to plot the column name rear force Z. Oh, that would actually just be plotting Y. We could do X, Y, or we could just plot one time series. We'll just plot one time series for simplicity's sake. because we'll get into advanced plotting later. And we could go ahead and assign a Y label as force in newtons. And we could assign an X label as time. Actually, I do have it here that we can plot time. So we could go ahead and just plot Y, but if we want X and Y, there's also a column name in trial force data for time. So as X we'll plot as time, as Y we'll plot as root force Z. So I go ahead and play that. Here's my plot of rear vertical force. As many of you have experience in MATLAB, MATLAB is a very index-based coding platform, but in Python it can be a little bit more difficult, so I wanted to spend some time on how to index your time series data. So I'm going to start out by finding a single point where I want to find max rear vertical force, and I will assign that as an object. So to find max force, I will use the max function of trial force data rear force Z. And we could keep looking into our Jupyter notebook to see our output value, or I could just go ahead and say, I'm going to print max rear force Z. And if I run that, my max force is 1,497 newtons. Now, if I want to know the exact frame when this happens, I can make an object here, the frame of max rear force Z. And I can say, I can use the NumPy module and say numpy.where. And I want to find out where trial force data rear force Z equals exactly the same function as I did before, max trial force rear force data. So if I go ahead like this, and I want to also print the frame that this occurs, and if I run this, we have a max force of almost 1,500 newtons, and this is occurring at frame 999. And if I want to know the time point, or like what time this is happening, say I can set an object time of max rear force Z, and I can say trial force data of time, and what that time is exactly at the frame of max rear force Z. And I could go ahead and also print time of max rear force Z. It doesn't like what I did.
Oh, I think maybe 0.
Here. Oh, you're right. So this occurs at 0.925 seconds into the trial. And we could go ahead and do the same thing for max touchdown force, just to show you again exactly how this would work. I'm going to do it because we're going to use these data values later for plotting and storing. If I wanted to look for the max lead force. I can say max trial force data of lead force Z, and find exactly where the frame that this occurs. Using numpy.where. We want to know where trial force data of lead force Z equals exactly my syntax for defining max force. And then the time that this occurs, time of max lead force equals trial force data of our time variable at the frame of max lead force Z. And we can take a look at all that too. We can print max lead force Z, frame of max lead force Z, and time of max lead force Z, which is 2,484 newtons at frame 1,300, which is the time point 1.20 seconds into the trial. I'm going to do one more real quick because we're going to use it later, but I'm going to start speeding through this a little bit so we make sure we leave time for you guys at the end to ask questions. And I just want to find lead foot contact and the frame that occurs so we can plot it later. So frame of initial lead foot contact equals numpy.where
And we're just doing one trial. Yeah. So he filtered down to just session trial 1031_2 earlier. Yeah. So that was one individual pitch.
And so what I'm doing here is I'm looking at the entire time series of lead force Z, but I'm looking at a smaller subset of that. So I'm just looking from frame of 0 until the frame where max force occurs. And I'm trying to look for when newtons drop below 20, or actually greater than 20. The force data is positive here in the Z value. So this can also help you by looking at smaller sets of the time series data to identify key points. Yeah, so when I run this, actually I can show you. If I do it without the zeros and I print this, it has an array, and within the array there is a vector, basically a numpy vector of all the values, and then there's another input here that assigns the type of the variables that are within it. And if I were to just take this frame initial lead foot contact and try to input it in later, I would be basically trying to put in all this information, but all I really want is the very first frame or the very first value that's within this array. So in this case, it's telling me within the array, the first part that's within the array, all the frames where force is greater than 20 newtons. But I just want the first frame that's above 20 newtons because I know that that's when foot contact would be defined. And so that's why I'm putting the 0 zeros into here. Before I forgot it and we ran into an error. That's because it was pulling more data into this function than what I was intending to do. I also want to go through filtering. There are a number of things that we need to define first for our filter. We need to know the total number of frames, and we'll do that by using the length function. And we want to know the length of the trial force data time column. And we need to know the total time. And we can do this by trial force data time. And Python is all zero-based index, but if you take the length, it gives you one more value than what you would expect. So we need the time at the last frame, which is total frames. But we have to say total frames minus 1. We have to set the sampling frequency. And we'll do that by making it the integer of total frames divided by total time. We need to set the cutoff frequency. We'll make that 50 in this case. There's something called a Nyquist frequency that we need to define for this function. Just set that at 1/2. We need the order of the filter. We'll do that as 4. The cutoff frequency is a calculation of cutoff divided by the Nyquist value. And then we need to set our filter, which provides us 2 values, B and A, in this case. And we do this by using the signal function .butter for a Butterworth filter. And the inputs are going to be N and FC. And then we can actually apply that filter that we just created, the B and A values, by saying lead force equals signal dot filtfilt with the inputs B, A, and we are putting a filter on trial force data lead force C. Screw that up. Okay. Nyquist needs to be 1/2 times the sampling frequency. I missed that. So lead force will be our object that is holding the filtered force data. And we can, applying the filter was this here. We don't confuse anybody. And now we can take the derivative and we can also integrate our data that we filtered. We're going to start off with lead impulse equals, we can use the integrate function. And within the integrate function, there is one called cum traps, QUMTRAPZ. And we are going to integrate our filtered lead force by our trial force data, our time variable. And then we can also find the rate of force development by taking the derivative. So lead rate of force development equals, it's a NumPy function called gradient. And we are going to derive lead force by time. So if we wanted to find like max lead rate of force development, FD, we could go ahead and use, you can do a max function, or you can do it a different way too. You could say lead RFD dot max. There's 2 different ways to apply a max function. And if we go ahead and print that variable, Max lead rate of force development is this really large value. I want to quickly show you how to store a time series into a CSV file because there is a lot of use for that typically. So if we use the pandas function, that data frame, and within there is a to CSV function where we need to use our curly brackets and say define a variable called time. Using the colon, we define time as a list of, I'm actually skipping the first part, but that's okay. Trial force data of time. And we also define our force with a colon as a list of trial force data, the lead force Z. I'm actually doing 2 time series now. We'll just skip a single time series to save some time, because I think most often you'll probably be storing multiple time series anyways. And then using the okay, I see what I did. So first I need to create a data frame. I missed a line here, and we can say save CSV equals, so setting an object to this data frame that we're creating. Oh. So now I have this object save CSV, which is a data frame of time and force. And I can use the pandas module data frame, now doing the to CSV. And we are saving our save CSV object, and we can save it to a location that we wish. I'll do C users, Alec Miller, desktop, ISBS 2023 folder, and I'm going to call this a force time.csv. If I go ahead and run this and I go open that folder, now here's my force time Excel that has time and force. We are really running out of time, and we want to leave questions for you guys. I'm going to skip our key metrics and storage, and I think we can skip advanced plotting too. I think we got through a lot of key points about working with time series data, so I think we could call it there. We will make the codes available online for you guys to access and play with. So don't worry too much about storing key metrics. It's pretty much just calculating discrete points, like we already did, max lead rate of force development, and just assigning a name to that variable and storing a CSV file. So it's pretty similar to what we showed here, actually. So we're not missing too much. And when it comes to advanced plotting, there's actually what I could do quickly to make this a lot faster is we have our other codes here, and I could just quickly show you what this looks like. Here's our advanced plotting. Does it pull a different?
You might need one.
Oh yeah.
So.
But this code basically goes through how to shade colors under the curve, how to set vertical lines at key time points. So we have one at like max landing force here, and also at one at like max rear push off. And we can also put in text objects to define like what we're color coding our plots. And here we also plotted 2 time series data. So we'll make this code available. It's not too complex. We hit the basic plotting, and you can take a look at this for more advanced plotting. So we will wrap it up there and open it up for questions. Yes.
I think to where it's was over 20 units.
Yeah.
This is just like one cycle. So for like people are walking cycle, I hope that to find all the instances of field strength.
Yeah. So actually, we could probably use that section of code. I'll show you just a brief example of how you would do it. So you would use a for loop, and you could say like for session in our trial for, or actually it was our master force data, the session variable.
Are you talking about within an individual trial, multiple occurrences, or?
Yeah, you have like a CSV file, header vertical force, but it's over like, I don't know, a minute, and you have multiple tracks.
Yeah.
Yeah.
Not moving through different sections.
Yeah, that's a pretty complicated one, but I've been able to work through it before. So basically, like for our time series data, actually for each value in our time series data, in our time series, if I could spell correctly. What you want to do is say time series, and you want to index value +1. And you want to compare this to the value before and the value after. So basically what we want to do is time series value +1. If that is less than time series value, which is also less than time series.
So you're right to where like if it's a little bit below between 15 and 25, it's 20 minutes.
Oh yeah, you could do it. You could do it like that too. I guess I would. Yeah. So I misunderstood a little bit. What I was trying to code was if you have multiple. Let's say it didn't go back to 0. You could easily do something like that.
So if do you have like multiple force plates where each foot is hitting one? Yeah, and so there's a lot of approaches to it. You could use the NumPy where function and then look at that will return all your indices where it's above a certain threshold, and you can trying to think of how I would approach it.
I guess
because whatever your threshold is, that's like your boundary, and there's modules in Python that can automate threshold crossing detection for you. And that's kind of how probably I would try to attack it. That or some kind of like, I need a certain number of frames between a boundary threshold crossing before I count it as a new field strike.
But one way that I've done it before too is if it's from one force plate, for example, and they're landing and picking up, landing and picking up, you can say exactly what we did when newtons are above 20. And I printed the list that creates, and it tells you every frame that's above 20. Here we're incrementing by 1 because every frame is above 20. But let's say that it drops below 20 and later goes above 20 again. We can analyze this object to see where like value +1 minus value is greater than 1. So basically analyzing where this frame jumps more than an increment of 1. And that's how it can help you define where these multiple foot contacts are happening. Sure.
There's like max value of frames, and then you save it, or you say that's an object name, and then you code it again. But I guess could you put it where it you have like equals max? Yeah, there you go. Okay.
Yeah.
So on top you find it already.
Yeah.
And so if you have to rewrite the, like, code, can you just replace that with max for Z?
Yes, you
You
can.
can, okay.
You can. I've ran into errors doing it that way because sometimes Python will round the value if it has too many decimal points or something along those lines. So I typically make it equal to the function I just used because it's a more reliable syntax for that task.
You could maybe save it up to a certain decimal place, then just be consistent.
So if, let's say if this max rear force, if it did somehow round that value, you will never find it with the equals value in that time series. Because it has to literally be exactly the same characters with the same numbers. There can't be one small difference, otherwise it won't work.
Thank you.
Yep. Any other questions or something that we could help somebody find a solution for? Wendy?
Yes, more generally speaking, since so many folks know MATLAB, but
Yeah, one of the biggest ones is indexing. So MATLAB is one-based indexed. So the very first value within some vector. So when we use our time series here, for example, trial, max, force data, rear force, Z. If I wanted to look at frame number 1, in MATLAB we would say 1, but Python is zero-based indexed, so the very first value would actually be 0. And figuring out this, it might seem like that's a really small change, and it might seem easy, but I guarantee if you're flipping from MATLAB over to Python, that this will give you a hard time. So just knowing that in general will be really helpful. Also, functions that occur in MATLAB might not exist in Python. So I know like finding local mins or local maxes, there's a really easy function for that in MATLAB. But in Python, you basically have to create it yourself in a for loop. So that will also be difficult, that they're not a direct translation to each other, but you have to find your way around to accomplish the same types of tasks. Also MATLAB, just they update their functions and everything, but in Python, you can have different versions of your interpreter. So here we're using Python 3.8.5, and packages might work differently or might not work at all in different Python versions. So that's also something to keep in mind too. Do you have any other tips for MATLAB users trying to convert to Python?
It's been such a long time since I was in MATLAB. Yeah, indexing was the big one for me.
So how do you know which Python? About assessment the best fit?
If you're trying to accomplish a certain task, maybe if you're using like OpenCV, for example, which is a more advanced image processing package, it's able to do certain things in older versions that are now deprecated, so they don't work anymore, but you might still want that function to work in your code. So you might want to scale back your Python version to be able to use that certain feature within a certain package. I would say just go with the most recent version and you should be okay. But if you get to that point, you'll probably be pretty advanced at that step, and you'll be able to scale back your version and make it work. Mike?
In MATLAB, I used a GUI to cut the long recording time series data trials. Is something like that possible in Python?
Do you know of a feature in Python where if you had a plot, you could like select a time point and it tells you like that value or frame?
You'd have to your own interactive GUI. Yeah. I don't think anything like that exists. You'd have to hard code it.
Yeah.
You can build really amazing user interfaces with Python. PySimple GUI is one that I've used a lot for building GUIs so that our interns can interact with our databases, for example, instead of having to learn SQL directly.
Sure.
But you have to build that GUI yourself. And so you could build a custom application in Python to then be able to like point, click, and trim based on visual, but you'd have to build it. Yeah.
That's a good question. More times than not, it's usually having to kind of build it yourself. All right, then we'll wrap up the session. Thanks everyone for joining. I hope it was helpful for you. And if you have any questions, feel free to reach out to us. And we will post on the ISBS app or website where you can access this information. Thank you, everyone.